Hello students, this is Mr. Allen, and we are going to continue our discussion with limits. And today we are going to be looking at section 1.4. Section 1.4 is on continuity and one-sided limits. Our objectives for today are to determine continuity at a point and continuity on open and or closed interval. We want to be able to understand and use one-sided limits, and we'd like to be able to use and understand the intermediate value theorem. So what I have here is I have three different functions, and each of these functions represents a graph that is not continuous. Not continuous. So when we think of continuous, intuitively, you would probably think of being able to draw a curve, something maybe like this, without lifting your pencil. So if we look at this first example, clearly we can see that to draw this curve, we have a problem right here, right? We've got a problem there and we can't draw that curve without lifting our pencil. This second diagram, we can see that we also have an issue where, you know, to draw this one, we would go to here, but then we have to lift our pencil then to go to here. And then finally, we have an example of one where, again, we've got an issue. So notice that in the first diagram, the function's not defined at C. In the second example, the function's limit is not defined at C. And in the third example, we have a function whose limit is defined, but it is not equal to the value of the function. So this brings us to our definition of continuity at a point. Continuity at a point for a function. So for a function to be continuous at C, it has to meet these three conditions. And when I give you an assessment, I'm going to ask you for these three things. F of C has to be defined. The limit of f of x as x goes to C has to be defined. It has to exist. And then those two things have to be the same. If any one of these three conditions is not true, then it's called not continuous at that point. If all three of them are, oops, I think I left out of you there. If all three of those conditions are true, then it is continuous. And then right below that, we've got the definition of continuity on an open interval. So if we consider an open interval that contains some real number C, if f is defined on that interval, except possibly at C, and if f is not continuous at C, then it has something we call a discontinuity, which kind of makes sense, not continuous discontinuity. These types of discontinuities can be referred to in two different ways, removable and non-removable. A discontinuity C is removable if f can be made continuous by appropriately defining f of C. And I'll do examples of both. In fact, let's just go back to the very first diagrams we had. This first example is an example of a removable discontinuity. And the reason it's a removable discontinuity is we know we have a problem at f of C. F of C is not defined. So if I just define C to be, I don't know, let's say that f of C is whatever this particular value is so that it plugs up that hole, then we're good. So that would fix it. That's why it's called removable. We could remove the discontinuity. Similarly, over here, if we took this, again, we've got a hole there. If we took this point and we were to move it up to where that hole is, we could fix that. That's a removable discontinuity. Part B, though, is non-removable because you can't put a point here big enough to fix that hole. And you got to keep in mind that the size of a point is actually infinitesimally small. So let's look at the discontinuities here, and I'm just going to do these graphically, and I might do a little bit of notation just to show you. So we've got three different functions. Function f of x is 1 over x. That graph looks like this right here. So I've already included that. It's this curve. It goes like this, and then it goes like this. So This function's continuous, except it is discontinuous. It's discontinuous at x equals 0. And that should kind of make sense because if you plug a 0 in there, you're going to get 1 over 0. Now, is this discontinuity a removable or a non-removable? Well, let me ask you a question. Can you somehow magically put a point in there to fix it? The answer is no. So this is a non-removable discontinuity. The reason you might say that this is discontinuous there is I would just simply say that f of 0 equals d n e. That's why it's discontinuous. It's continuous everywhere else but at 0, at x equals 0. Okay, so now I need to erase this. Let's go ahead and look at our next graph. So our next graph here, get rid of all of this, is the function x squared minus 1 over x minus 1. Now this goes back to something we did last week. Hopefully you're thinking, oh, wait a minute, I could factor that. So that would give you x plus 1 in the numerator and then x minus 1 in the numerator, which then we could cancel these x minus 1s. So now here's a tricky thing, and it's actually impossible to see that on this graph. But guess what we've got right here at x equals, oh, I'm sorry, not at x equals -1. At x equals 1. Guess what we've got there at x equals 1? Guess what we got there at x equals 1? Well, at x equals 1, this function has a hole. Because if you plug 1 into this, you're going to get 0 over 0. And if you were to plug this into your calculator and you looked at the table at x equals 1, it's going to say error. Because there is a hole at x equals 1. This is a removable discontinuity. So I'm telling you that the limit as x goes to 1 of g of x is 2. That is a true statement. The predicted y value when x goes to 1 is 2. However, g of 1 is d and e. So this is a removable discontinuity. So this is a removable discontinuity. So that's the second example there. And the third example is this sine curve function, which I'm hoping that you're familiar with. Does it have any discontinuities? Well, of course, the answer is no. The domain of sine x is all real numbers. And it goes now, the range is from -1 to 1, but there's no problem. There's no holes in this. There's no jumps in this. There's no gaps in this. This function is completely continuous on its entire domain. Furthermore, we'll talk about that a little bit more later. Let's talk about one-sided limits now. So one-sided limits, and I've kind of probably hinted about this a little bit before now, it's just a notational piece. And here's what we're talking about. In fact, let me just talk about this. When you see, and I'm going to just make one up here. Let's say I write the limit as x goes to 2 minus of f of x equals, let's say, 7. What I'm telling you is if we take the limit as we come in from the left of 2 for the function, then the predicted y value is 7. And then another way I could write this, a different type of one-sided limit, is I could say the limit as x goes to 2 positive of f of x. And let's say that that's equal to, I don't know, 10. So the way you would write that is this notation right here. So when we come in from the right, so if we came in from the right side of f of x going to 2, that turns out to have a limit of 2. So the left side's going to 7, the right side's going to 2, so the limit doesn't exist. So this is the notation, basically, that we're going to use to determine if a limit exists or not. Now notice that I have the word and here for this theorem. So this is what the theorem says. A function has a limit L when x goes to c if the left-sided limit equals L, some number L, and so does the right side of the limit. And we've already been talking about this. It's the predicted y value. It has to come in from both sides. It's just now we're giving you some notation. Continuity on a closed interval. So here's where we got to be careful, and this is the whole reason we have to introduce these one-sided limits, even though I think they're helpful anyways. Clearly this function's continuous on all the points here in the middle, right? But what if we just talk about this point here on the right or on the left-hand side? And I want to argue somehow that this function is continuous from A to B. Well, we just talked about that in order for a limit to exist, it has to exist on the left and the right, okay? The problem is this function doesn't have anything to the left of that point. So when we talk about continuity on a closed interval, basically what we're saying is this. We are saying that on a closed interval, when we're talking about this left endpoint here, we are only going to worry that the limit coming from the right of the function is equal to f of a. And then when we're on the right side of the function, the right endpoint, we're only going to worry about coming in from the left. So let's look at an example here, and I think I've actually got much of this worked out. So we're trying to figure out the continuity for this particular function here, which I'm hoping that you're familiar with. It kind of comes from this equation that we used the other day. I'm running out of room here because of my little camera thing. I'm going to scoot that up. Remember the other day we did the question with the cylinder, and then I solved it to solve for y. That's basically what this is. So what is this? This is a circle. It's the upper half of a circle with a radius of 1. And we want to discuss the continuity. So this particular function has a domain that goes from -1 to 1 because that's what the radius is. At all points in the open interval from -1 to 1, it's continuous. There's no issues. There's no issues with this function as long as we're between 1 and -1. Where we run into issues is when we start getting close to either the -1 or the 1. So let's look at a picture of that. So here's the picture of our function right here. So that is the upper half of a circle with a radius of 1 with a center of 0, 0. So we need to check those endpoints. So if we do the limit on the right over here at -1, now notice how we wrote that. Limit as x goes to -1 plus of our function. Well, that's equal to 0. Where would you predict the function's going when x goes to -1? Well, you'd predict it to be going to 0. What is the value of the function at -1? Well, that's also 0. You'll notice that those two things are the same number. So we are saying it's continuous. And then you could play the same game on the right-hand side. So we can conclude that f is a continuous function on the closed interval from -1 to 1, which is, I think, kind of intuitive. Here are some properties of limits. These are similar to the properties we talked, I'm sorry, these are the properties for continuity, sorry. These are the exact same properties that we talked about with limits back in section 1-2. It's just now we're talking about continuity. So, oh, actually, I'm sorry, these are the properties of limits, so it is the same thing. So the properties of continuity basically all apply. So now let's go ahead and describe the intervals on which this function is continuous. And I'm just going to do tangent x here. I hope that you're familiar with tangent x. The curve for tangent x looks like this. So there's the curve. We know that it has vertical asymptotes every pi units. So there is a vertical asymptote here at pi over pi over 2, negative pi over 2. So that's what this one is. There's also a vertical asymptote here when x is equal to pi over 2. And then there's going to be one at 3 pi over 2, etc. So what we've got is we've got continuity over an open interval. So for example, let's do this middle curve right here. It is continuous on this open interval. Now my question for you is, why is it not continuous on the closed interval? And it should probably make sense if you think about our definition of limits. Finally, today we want to look at the last thing here, which is the intermediate value theorem. You will hear me refer to it as IVT, which is an abbreviation for intermediate value theorem. The intermediate value theorem says that if you have a function that is continuous on a closed interval, and f of a does not equal f of b. In other words, they're telling you that the endpoints are not at the same y value. And k is a number between f of a and f of b, then there has to be at least one number c in that interval a to b such that f of c is equal to f of k. Now that may sound like craziness to you, but let me just explain this to you. Let's say that I tell you that I've got a function that's continuous from this point to this point. Sorry, it's actually very difficult to draw points on here. So that point to that point, would you guys agree that's continuous? So let's call that f of x. And let's say that f of, let's call this over here, let's say that this is x equals 10, and this over here is x equals 0. Let's see at f of 10 is, I don't know, let's say it's 5. And then over here, let's say that f of 0 is, let's say 1. So this point over here is at 0, 1. This point over here is at 10, 5. Continuous curve, right? Would you agree that f of a does not equal f of b? In other words, f of 0 does not equal f of 10. Oh, no, they don't. This one's 1, this one's 5. Those are not equal. My claim is if you give me a value of k that's between 1 and 5, so let's say 3.271, would you guys agree that that is between 1 and 5? The claim is by the intermediate value theorem that there has to be some, this is the k value, there has to be some value c here in the middle where that function has to be 3.271. In other words, you can't go from 1 to 5 and somehow skip over 3.271. To get from 1 to 5, you somewhere had to hit 3.71. And this is based on continuity. It has to be continuous. So for example, an application of this would be, let's say a boy is 5 feet tall when he's 13 years old, and then he's 5 feet 7 tall when he's 14 years old. Then for any height h between 5 feet and 5 feet 7, he must have been that height at some time t. So question I have for you is this: was he ever 2 feet 3 inches between being, what was his age, 13 and 14? Well, yes, he couldn't have just magically went from 5 to 5 feet 7 and skipped over 5 feet 3 inches. Somewhere in that growth period, some instant of time, he was exactly 5 feet 3 inches. The intermediate value theorem guarantees the existence. This is another existence theorem, just like MVT. And since it's an existence theorem, it does not tell us where C is. You would have to figure that out. It also does not tell us how many. Could be multiple times. So for example, if we look at this curve here in this picture, in this diagram, so the K value here is whatever it is, let's just leave it as K. We can see that from A to B, it hit 1, 2, 3 times. It hit 3 times that value of K. The intermediate value theorem does not apply if we have a discontinuity. So again, if it's not continuous, you could have skipped over some values.
Freshman, if you have a problem or issue with your Chromebook,
okay, I need to
you may report to the
keep going here, but
right
Mr.
now.
Miller's talking.
Issues with Chromebooks. Thank you.
Okay, so we're going to do the intermediate value theorem for this function here, which is x to the third plus 2x minus 1. And we're going to say that it has a 0 in the interval from 0 to 1. So first of all, the interval we're looking at here is 0 to 1. So that tells us that A is 0 and B is 1. So what is f of 0? Well, f of 0 is negative 1. I'll leave that for you to check. You just plug in 0. It's very simple. F of 1. Well, f of 1 is going to be, well, I think that's going to be 2. Because if you got 1 to the third, that's 1. Plus 2 times 1, which is 2. So 1 plus 2 is 3. And then minus 1, so that'd be 2. So here's my question. Is our K value of 0, is that between -1 and 2? And the answer is yes. So I am telling you there has to be some value C for which the function has the value of 0. And this would be by IVT, because this function is continuous. Has to be. It has to go. In other words, it has to go through the x-axis. I guess we could figure that out algebraically. I'm not sure what we're doing on time now. I got kind of oh, here we go. We can just look at this. We can see that here we've got our curve x to the third plus 2x minus 1. And so that was that x value of 1 with a y value of 2. And here's that x value of 0 and a y value of -1. And we're good to go. Let me go back, though, here and just let me, I think I'm going to stop. I think we're about where we need to stop. I'm sorry, guys. I got distracted with that announcement.